Physicists like Albert Einstein and Stephen Hawking dreamt of capturing the intricate dance of the cosmos in one grand equation, a theory of everything. Sounds epic, right? But here's the kicker. Merging the vast expanse of the universe with the tiny realm of quantum particles has stumped scientists for over a century. In this video, we're peeling back the layers of this cosmic conundrum. We'll explore the elusive quest for a unified theory, delving into the enigmatic world of quantum mechanics and the vast expanses of space. Get ready to have your mind blown. Join the conversation by sharing your thoughts and questions in the comments below. And hey, if you're as captivated by the cosmos as we are, don't forget to hit that subscribe button. Have you ever been lying in your bed thinking about everything? I mean, of course, the grand unifying theory of everything. Let's talk about the big one, the theory of everything. If you're new to this, think of it as the ultimate puzzle in physics, the big kahuna everyone's after. Right now, there's a big gap in our cosmic understanding, and whoever cracks it will open the door to a whole new scientific era. This quest sparks some serious debates among scientists, each vying to make their mark in history. So, what's all the fuss about? Picture this. The rules that govern the vast universe we see don't quite fit the tiny world of atoms and particles. Up here, we've got gravity and special relativity doing their thing. But down there, it's a whole different ballgame, with strange stuff like probability waves and quantum quirks. Let's break it down. Up here, particles seem solid and real. But down there, it's a whole different story. They're just probably hanging out. Here's the kicker. Both views have their merits. Quantum physics nails the tiny stuff, leaving special relativity in the dust. But here's the catch. Quantum physics struggles with the big picture. Planets, gravity, the whole shebang. And special relativity? Sure, it's great for satellites, but it's clueless about the quantum weirdness lurking in the micro-world. So, what's the deal? Scientists reckon there's gotta be a grand theory out there, a one-size-fits-all explanation for everything, big or small. But here's the thing. Finding it will take a seismic shift in our thinking, like when we went from Newton's apples to Einstein's spacetime. So, why not roll up our sleeves and give it a shot ourselves? Get ready, folks, because today's video is all about tackling the big questions, literally everything. But before we dive in, let's set the stage. Now, fair warning, the ideas we're about to explore are pretty out there. But hey, they're rooted in solid theory, so stick with us. Trust us, by the end of this, you'll be nodding along seeing the puzzle pieces start to fit together. So, buckle up and join me on a cosmic journey to uncover the secrets of the universe. Now let's be real. Squeezing the entire theory of everything into one video? Not gonna happen. But hey, we can lay some groundwork, right? We're kicking things off with a model, not the runway kind, but a conceptual framework to make sense of it all. Quantum physics is our starting point, a realm where the math is rock solid, but the explanations, well, let's just say they're a bit fuzzy. What's up with probability waves and waveform collapses? It's a head-scratcher for sure. So, here's the million-dollar question. What do all those fancy equations actually mean on the tiniest scales? How does it all connect from the smallest particles to the grand cosmos? Let's dig in and find out. Now, let's take a peek into the past, where others have ventured in search of these very answers. One contender that caught science's eye was string theory, a theory that started with a bang in the 70s, but ended up leaving us scratching our heads. So, what's the deal with string theory? Well, instead of thinking in terms of particles, it shakes things up by suggesting that everything is made of these teeny tiny strings. Just like guitar strings, they vibrate and dance, creating waves and harmonies. And here's the kicker, this idea sheds light on some of the quirks of quantum mechanics, hence the name quanta. At large levels, you might not notice this. If you have a light, you can have the brightness of it by putting a semi-transparent shade in front of it. You can do that again and again and again. However, if you keep doing that until you are at a small enough level, suddenly you can't go any further. In the quantum realm, it's all about being whole. No half measures allowed. Think of it like this. You can have one photon, or you can double that to 2, but there's no in between. The universe prefers its stuff in neat, tidy packages. Take electrons, for example. They're picky about their energy levels. It's either this one or that one, no in between. Why? That's the million-dollar question. Now, here's where string theory struts its stuff. Just like plucking a guitar string, strings in this theory can vibrate in specific patterns called harmonics. Picture it. The first harmonic is like a smooth wave, while the second has a stationary point in the middle. You can keep adding more harmonics, each packing more energy, but you'll never catch a half harmonic in the mix. It's all or nothing, just like in the quantum world. String theory didn't stop there. It took things up a notch. See, particles aren't just empty shells, they're packed with info. Imagine this, the way strings vibrate, it could hold the key to unlocking all that info. If a string wigglies up and down, it might tell us something about the particle's charge. But flip that string to vibrate side to side, and bam, you've got another piece of the puzzle. And here's the kicker. The more directions these strings could wiggle in, the more info they could pack in. It's like unlocking a treasure trove of particle secrets with each vibration. Now, if you're a whiz in 3D space, you might raise an eyebrow at this point. Once you've covered up, down, and side to side, there's not much wiggle room left for new directions without messing with what's already going on. And here's the snag. Particles need to be able to change their properties without stirring up a hornet's nest of consequences. Like, you should be able to tweak mass without messing with charge, right? So, string theorists put their heads together and came up with a clever workaround. Let's just add more dimensions to the mix. Enter 4D space, then 5D, and even beyond. But here's the kicker. The more dimensions we tack on, the more skeptical folks get about string theory being the one to tie it all together. In the world of academia, there are different flavors of string theory floating around. Depending on who you ask, you might hear about electrons, quarks, and all the subatomic gang being described in either 26, 21, 11, or 10 dimensions. Yeah, it's a lot to wrap your head around, and things can get pretty tangled up. But here's the thing. The groundwork for 4D space is already laid out. Think about it like this. If you're a flat 2D creature, you can't see that third dimension. And if you're a 3D being like us, that fourth dimension is a bit of a mystery too. But just because we can't see it doesn't mean it's not there. Here's a mindbender for you. Despite chilling in our 3D space, we're still zooming through time. That's a whole other direction we're moving in, folks. So, what do you make of all this? Drop your thoughts in the comments below. And hey, if you're as intrigued by all things space and science as we are, hit that like button, share this video with your fellow enthusiasts, and don't forget to subscribe for more mind-blowing content.